Okay, so in terms of differential equations, these are the three different types that we've sort of done already. And what we're really doing is looking at a fourth type. So this was a separable equation where we could take the dx over here and we had y squared to y equals x squared plus 2x dx, and then integrate both sides. Here was one of these ones where we could use a substitution, and the substitution that we often use is that v equals v equals x over y. And this was where we use that integrating factor. So we've looked at these three different types of differential equations, and this is the one that we're looking at now, where it has the form y double dash plus 2y dash plus y equals 0. And we're sort of looking at this in terms of a quadratic. And we're having a bit of a guess, but it's not really a guess. It's a very, very educated guess as to what the answer will be. So let's see how that works first. So if we've got this equation, y double dash, or the second derivative minus 2 times the first plus y equals 0, let's suppose the answer looked like this. Then suddenly you've got that y dash is going to be 12x cubed plus 2, and y double dash is going to be 36x squared. So when we substitute these three things in, is there any way that we can get 0? We've got 32x squared minus 2 times 12x cubed plus 2 plus this 32 3x to the power of 4 plus 2x. And it's never going to come down to something nice, because you've got this x to the power of 4 here, and you can't cancel that out with anybody. So we sort of know that this cannot be a general solution to that. So what could be the general solutions? And that's where this guess sort of comes in. Now, this may not be the general solution, but at least it's got a chance. If y equals 2e to the 3x, then y dash equals 6e to the 3x, and y double dash equals 18e to the 3x. So although this isn't the solution, 18e to the 3x minus 2 lots of this is minus 12e to the 3x plus 2e to the 3x. All I've done is substitute. At least this gives us a chance. At least it gives us a chance of being the solution. So that's why instead of guessing a 2 out the front, we look at C1e to the 3x. Okay? And that is our general solution. And then we find out what C1 could be. The other thing that it could possibly be, or the other chance that it has, is sines, a combination of sines and causes. So I've done the derivatives here, and you can see that y double dash is going to be minus 2 sine x plus cos x, minus 2 lots of this, so it's minus 4 cos x minus sine x plus 2 sine x minus cos x. And again, I can see that that's probably not a solution, because the minus 2x here cancels out with the plus 2x, and the plus cos cancels out with that. But you've still got something, but at least it's given us a chance. So again, that's where we come across this whole idea of looking at that as a general solution, plus C2 cos x. And the next thing is, when we're solving these, is that, as I said, we look at them in terms of a quadratic. So if we've got something like y double dash minus 3y dash plus 2y equals 0, if we can let if we change this to lambda squared minus 3 lambda plus 2 equals 0, then this is going to have three different situations. This could have two roots. It could have equal roots, or it could have complex roots. And what we basically get is if it's got two roots, then our guess or our starting point is CE to the AX or C1 and C2E to the AX in terms of our what our values for alpha and beta. Maybe it's a better way to look at that. If they are equal roots, and we want solutions that aren't linearly dependent, so we look at C1e to the alpha x, if alpha is the root, and the other one is C2x e to the alpha x, where alpha is the root. And if they are complex roots, that's where we get the situation where we're looking at sine alpha x plus cos beta x sort of thing. But they're the three situations that we have. And that's why this system, it's a new system to solve slightly different looking differential equations. Thanks.